And I'm sure I mentioned in the video as well that when we're talking about washers, we're talking about like the hardware store washers, like the things that go with bolts, as opposed to like a clothes washer. So these little washers will stack up in various shapes and patterns and form these solids that have holes in them or concavities in them. And the formula, of course, is pi integral r squared minus r squared. So this is basically, essentially, honestly, it's the disk method where you take a big disk minus a little disk. It's really all it is. So please don't think of this as something totally different than the disk method. It really is the disk method just adapted to something that has a hole in it. So we can draw pictures, and well, maybe we should have Cameron draw pictures because Cameron proved herself to be pretty stinking awesome at drawing pictures. This would be also a time where maybe Play-Doh is appropriate. And while you're working on some of these, I might go see if we have some workable Play-Doh that we could use to make some of these shapes. And I especially would think about using that when we get into our final topic, which is volumes by cross-section. So see how this goes. All right, so in the video we did A. We have not done B, C, or D yet. So let's read this over again. It says region P is bounded by those two graphs. Use region P to answer the following questions. So I'm going to scroll down, and I'm going to attempt to draw region P. I'll do this off to the side. So the first part is a parabola, I believe. So we're going to make this like so. So that would be y equals x squared. And then the other one is y equals root x. Is my short-term memory doing okay? Is it y equals root x? Okay. So y equals root x looks something like that. And I'm just going to stop it right there because that forms my region. So that would be your region P, and I'll highlight that right here. And it looks something like that. So I think for all these questions, we're going to do stuff with region P. Going to rotate it around various things. And in part B, we are asked to rotate that region around the y-axis. So if we're going to rotate this around the y-axis, I always like thinking about it like this. Can you guys describe what kind of shape would result if we really did do that?
A bowl.
A bowl. Okay. What else could you say about it? A vase. The fancy kind. Yes, I like it. It would be a unique bowl, wouldn't it? Because the inside is like convex. So if this was like a cereal bowl, wouldn't you be like forever digging down there at the bottom? There would be like a little kind of a pointy bottom. You'd be like trying to get the cornflakes out of there or whatever. Say again? There you go. I was kind of thinking this almost looked like sort of a flower, kind of. It would be a very like uniformly smooth flower, kind of. But I can see the bowl concept for sure, and the vase for sure. Because this would definitely hold water, wouldn't it? It would barely hold water down there at the origin point, but it would hold water. So the principle for the washer method is exactly the same as the principle for the disk method. If you're revolving around some axis of rotation, then the representative rectangle will be perpendicular to that axis of rotation. So it would look something like this from a representative element standpoint. It would look something like that, and that representative element would be rotated. And can you see how, at least on that level right there, that would truly form a washer? You've got this extra space right in here. You've got that extra space that I'm trying to highlight. And so as that region gets rotated, wouldn't the space essentially be rotated as well? So it would leave you with that gap in the middle where your cereal would go or your flowers would go or whatever. Okay, so your first hint is this, as far as what you're supposed to do. You would look at this and ask yourself the question, when I rotate this region, would there be some sort of hole or concavity in the resulting shape or solid? And the answer is definitely yes. So that means we have to use the washer method. And so the washer method looks like this. I don't know. I know how I taught this last year, and I'm going to teach it the same way. But for folks that I did not have the pleasure of working with last year, here's what I do. And I got to be honest with you, I do this simply because for me, this works. I don't get things confused. I don't put things in the wrong spot. Here's what I do. Once I identify the washer method, I write V equals pi integral, and I don't put any limits on there yet. And then I put big parentheses squared minus little parentheses squared. Okay, the big parentheses standing for the big radius, and the little parentheses standing for the little radius. I mean, so just like a visual to remind me, there's two separate radii. One of them is the big one, and the other one is the little one. So this is how I started off. The next thing I'm going to do is I'm going to decide, is this going to be an integral that's in terms of dx or in terms of dy? And based on my picture, and maybe you have a picture too, we can answer that. What do you guys think? Dy, right? Because we're perpendicular to the y-axis. Yeah. So dy, y? Yes. Because we're perpendicular to the y-axis, right? So it's a dy, and so that automatically sets up a couple of other things. I can now fill in my limits of integration. So because it's a dy representative rectangle, I am not going to be accumulating from left to right, because that would be a dx rectangle, wouldn't it? I'm not going to be accumulating that way. I am going to be accumulating from bottom to top. It makes sense? Those representative rectangles will just accumulate from the bottom of the shape up to the top of the shape. Does that make sense? Okay, so then we got to figure out what those limits of integration would be in terms of y. So bottom level would be 0. Yeah, we're going to start accumulating at 0. And then we'll stop up there at the intersection point for the region. So we got to figure out what that intersection point is. And it is? Isn't it 1, 1? And so this is one that's kind of hard to mess up. We want the y equals 1, right? So if you just put a 1, you're safe because they're both 1 up there. And really that bottom left corner is 0, 0. So it's really hard to mess this up. But we want the y equals 1, not the x equals 1. Sound weird to say that, but does it make sense? Okay. So 0 to 1 right there for our limits of integration. And then finally I need to put in my radii. Okay, so the radius is the distance from the axis of rotation to the, either the inner radius or the outer radius. And my first radius is always going to be my big outer radius, the one that goes all the way to the outside of the shape. So I would say that that distance goes from right here all the way out to right there. So if I illustrated this with this purple line segment, it would be that distance there, wouldn't it? From the axis of rotation to the outer edge of this shape. So can anybody describe what that distance is or what that radius is? So you're going a little further than I wanted to go. I think you're right. Can anybody describe it in the most basic conceivable terms? No? Think about what I'm doing there. I'm picking at this because I want you to understand why. Say it again?
The higher function?
Yeah, but there really isn't a higher function here because we're doing right and left instead of up and down with the arrangement. So it would be more of the right function. I can kind of sort of live with that, except what if I moved my axis of rotation? Then the up, down, left, right could all of a sudden change.
Right.
So we want to be consistent, and I'm looking more for... So yeah, sure, it's farthest from that. You know what, that's like saying Jesus to every question in Sunday school. Concavity.
X equals 2.
Yeah, okay. So, think in really elementary terms. So if this were an Algebra 1 class and I said, how far is it from here out to there? It's not consistent, is it? Because depending on where you are, it's either going to be longer distance like that or a shorter distance like that. So how would you describe that distance?
X.
It varies, doesn't it? Depending on where you are? It varies. It literally is x, isn't it? If you think about it, isn't the definition of x, did you say that earlier? Was that part of a series of Sunday school answers, or was it well thought out? I'm sorry if I didn't hear you. Okay. But isn't that the definition of x, though?
Yes.
It's from the y-axis out to the right or from the y-axis out to the left. That's the very definition of x. So if you wanted to, I don't know that I would suggest this, certainly not as a final product, but you could say, okay, that distance literally is x, right? Because it's from the y-axis out to the outer edge. We're never going to leave it that way, are we? Never going to leave it that way because we know that everything in the end has to be in terms of y because it's dy. So this is where we go back to Blake's idea because he just says, hey, I think it's root y. I think it's good to know where that came from. So that outer function, that red one, the equation for it is y equals x squared. And so if that original or that bigger radius is x, then we need to put that in terms of y. We can do that pretty easily by square rooting both sides. You would technically get plus or minus root y. And the truth is, it really wouldn't matter because you're about to square it anyways. Well, I think in general, I'd just go with the positive side. So I'm going to go with that Blake had the right answer, but I wanted to make sure we understood WHY. Make sense? Does that seem logical to you? Maybe it already seemed logical, and that's great, but I just wanted to make for sure that you felt that way. Okay, and then the little radius, I will represent with a different color. How about bright green? So the little radius would stretch from the y-axis just to right about there. And so that is also what kind of distance? It's a different x, but it is also an x. It's depending upon the blue function. And the equation for the blue function is y equals root x. And so if I were to put an x in there, you'd say, okay, that's all well and good, but I know we're going to change it eventually. So what would x equal to for that blue function, the little radius? Wouldn't you have to square both sides? Yeah, so y squared. And so I'd put y squared right there. And we've got it. Does that make sense? Okay. You can obviously simplify this somewhat. Volume equals pi integral from 0 to 1 of y minus y to the fourth dy. And if, I guess at this point, you'd have to make a decision. Would you be using a calculator to approximate it, or would you be doing it on paper, pencil and paper, and getting an exact answer? I don't know the answer to that question because it goes both ways sometimes. Like this one would be very easy to evaluate without using a calculator, but sometimes stuff like this would be on the calculator section. Just kind of depends. If you look at that and you think to yourself, there's no way on earth I can do that, which I doubt any of you would actually be saying that. But if you look at it and you say, hey, maybe I could use the practice, take a couple minutes right here and let's practice taking this all the way through to an evaluation. If you're just like, I've done this to death, I can do this in my sleep, then just use Math 9 and we can all compare answers when we're done. Okay? So you make a decision that benefits you the most. So C says, got the same region P, but now we're going to be rotating around the line x equals 3, and often they'll give you like one more descriptor. They will say rotate it around and they'll tell you whether it's vertical or horizontal. So x equals 3, is it vertical or horizontal? That's the one thing I don't think it can be. Vertical, yeah. X equals is always vertical. My way of helping my Algebra 1 students remember it is I say if you tried to ski it, you'd get X'd out, right? If you tried to ski it, you'd say, why do I bother? Get it? X'd out, why do I care? This would be boring. For a workout, sure. But yeah. So anyway, if you have a hard time remembering it, I know some of my students are just like, I can never remember it. So that's just a way. You can come up with your own way. If it's better, use it. Anyway, so what we would do then is we would take that same graph and just change up the rotational aspect of it a little bit. Blake, my Algebra 1 students say the same thing. They're like, dude, no, I totally skied off this cliff. I'm like, yeah, I know, me too. I have skied off cliffs before. They were like of the 8-foot tall variety. So not particularly scary, not like hundreds of feet tall, but scary enough though. Oh, it was scary enough for me, but in the world of skiing, 8 feet is decidedly JV or perhaps freshman team.
My sister did like 15 feet at age 5 because she couldn't stop.
Who?
My sister.
But it was more of an accident?
Yeah.
Like, oh no. You guys ever ski at Jackson Hole? That is a very distinct possibility. There's like unmarked cliffs and rocks and obstacles all over the place. So you can't just like let them rip and be like, I'm good. Because you like literally might like ski off a cliff. Like, not a good way to end the day. Anyway, well, so she can at least say that, right?
Yeah.
I'm like extreme. I went off a 15-footer. Definitely higher than I've done. Okay, so there's the region again, and of course this time the line x equals 3, it would be over here somewhere. We shall say it's right there. We're rotating around that. So, you got your picture there, and the good news, a lot of time on my test or AP test, you'll just usually get the graph, or the calculator will be active and it'll be really easy for you to graph it. So please don't feel like you're going to have to remember every little detailed graph. I mean, it'd be good if you did, but most of the time that'll be given to you. So the first thing I want to do here is write in my representative element. Is this going to have to be a dx or a dy type rectangle? dy. This is kind of like revolving around the y-axis, isn't it? I mean, it's displaced from it, but it's kind of like that. So I've got to be perpendicular to it. That's the overriding principle. So it would look something like that. And it would be a dy rectangle, completely agree. So based on that, I'm going to go ahead and write out what I've got. As far as, well, and sorry, I did kind of skip a step there. Do you guys see how there's a gigantic hole in the middle of this? Like all this space right here? All that space is going to be rotated around as well, and so you're going to end up with a big hole in there, meaning you have to use which type of setup, which method? You got to think of it as washers, that's right. So we're going to say volume equals pi integral big parentheses squared, which stands for big radius squared, minus little parentheses squared. Again, that's little radius squared. And then as you guys said earlier, it'll be a dy rectangle. So I want to give you all just a chance to try this on your own a little bit, progress and proceed. Maybe if all the way to an answer, great, but at least try to get it set up. Give you a couple minutes to do that. So as far as the big radius, if I was going to illustrate that, here's where you want to just be careful with like rights and lefts and ups and downs, because I think sometimes we mess up our perspective on that. I would say that the big radius stretches from the axis of rotation all the way over here to this light blue function. Would that be fair to say? Okay. So that big radius right there, it's, you know, at first glance, it's kind of hard to describe exactly how far that is, because we're talking about that part, but it's measured from the vertical axis, you know, the blue part right there. If I can explain how I think about this, maybe this will help. You can also, if you have an idea of how you like to think about it, that's fine too. The way I do this is I look at the full distance and I say, to get back to the y-axis, I'd have to cover that blue distance as well as the orange distance, wouldn't I? To go from my vertical axis of rotation all the way back to the y-axis, I would have to do that. So I'm going to express my blue distance kind of using that concept. Wouldn't it be fair to say that this orange distance is an x distance? Okay. But then I know also that the full distance from here to here is 3. So if I know that the orange part is x and the whole distance is 3, how would I get just the blue distance? Do some subtraction, right? 3 minus x. So if you wanted to do that, you could write 3 minus x. But of course, we know it's dy, and so we're not going to leave it like that. So for that particular function, x would equal, is this the one, x equals y squared, right? So I would replace the x with y squared, and I've got it right there. And then similarly for the small radius, I'd be going from here to there. That would be the radius that I'm after. That's what I want. But then once again, I've got that x distance that goes from here to here. But I know the whole thing is 3. So to get the purple distance, I would go 3 minus the little green distance, so 3 minus x again. But this time it's a totally different x. So instead of writing 3 minus x, I could write 3 minus square root of y. Yeah, root y. So a general rule of thumb is this. If you've got a displaced axis like this, then to get your radius correct, you need to go axis of rotation. In this case, it's a 3. So axis of rotation minus the function in its appropriate x or y form, right? In terms of x or y, whatever is appropriate based on the dy or the dx. So axis of rotation minus function. You can actually do this in every instance, even if the axis of rotation is smaller than the distance on the function, because even if you get the order wrong, like the order in the subtraction wrong, what are you about to do? Square it. Yeah, so if it's supposed to be, like just for number's sake, if it's supposed to be 7 minus 2, and you write 2 minus 7, but then whatever you're going to do, you're going to square the result, it makes no difference on the order, does it? So that's why I say I always go axis of rotation minus the function in its appropriate form in terms of y or x. Final thing I'm going to do here is put in my limits of integration. We already did this on the other one, but aren't we going to accumulate from bottom to top again? So we would go from y equals 0 to y equals 1. Y equals y. I don't know what that was. And that's your setup. So once again, you could FOIL and do this pencil and paper and get an exact answer. You could always do Math 9. Did you guys get answers? And did this go okay? Did you guys do it right? Remembering this okay? Do you have any questions? I did let you just run with it for a while, and nobody seemed to be having questions. But okay, so did anybody get an exact answer on this one? Or did you all go math 9?
17 times pi.
Let's say again?
17 times pi.
17 tenths pi, okay. And does that go with the decimal answer some of you got, which would be, let's see here, it would have to be about 5 something? 5.34 what? Okay. Everybody okay with those? Okay, so the final one here would be D, and I think I'll just let you guys take this one from start to finish. So, give it a go. D. So this obviously twists things around a little bit. Did you guys have a picture relationship like that up there? Something like that? So this is different, of course. This means that we are going to be rotating around instead of some sort of a vertical axis of rotation, now it's horizontal. So that means our axis of rotation is not going to be like it was before. It needs to be like that. Meaning that when I write out my integral, everything is going to have to be in terms of which variable? Because that's a dx thick rectangle. So, so I think maybe I'll go ahead and do that. I'll write volume equals pi integral of big radius squared minus little radius squared, and they're going to be in terms of x. So maybe something like that. So sometimes there's some confusion on this as far as, just because you have this displaced axis of rotation, the -4, is that going to affect my limits of integration? So the fact that I've got that -4 down there, is that going to make me change the way I think about those limits of integration, or will it be the same?
The same.
It is the same. It is. So what we're going to do is we're going to say, instead of accumulating from bottom to top like we did on the last two, we're going to accumulate from left to right. And that accumulation would maybe look something like this, from left to right. So as far as the limits of integration go, this time they would have to be from x equals 0 to x equals 1, as opposed to the y equals 0 to the y equals 1. So I'll put 0 and 1 right here, knowing that those are x's. And once I've done that, I simply need to figure out what my radii are. Okay, so you could do this in a number of ways. If you did follow kind of that the way of thinking I just gave you, then here's what you would do, and we can talk about why this works. You would go, for the further away function, I would say it's -4 minus, and that further away function would be the blue function, so it'd be stretching from there all the way to there, and that is the square root function, so it would be root x, right? So it'd be -4 minus root x. And then for the closer function, the small radius, that would look like this, from here to maybe there. And so that would once again be -4 minus something, but this time it would be minus x squared, because that's the closer function. And notice I use, of course, the function in terms of x, due to the fact that it's a dx rectangle, instead of the function in terms of y like we did before. So what do you think? Any questions there? Yes, sir.
When we originally what we do is we did -4 plus root x. We actually got a different answer.
Yeah, -4 plus root x is no good. So let me explain a different way to think about this. You could think of this more spatially rather than formulaically. So here's what you could do. You could say, I'll do this in bright blue. So you could say, all right, from here to here, so in other words, from the outer edge to the x-axis, you could look at that and say, well, that's a distance of y, and y equals root x for that part. And then you could say, well, then to get all the way to the axis of rotation, listen carefully, it's a distance of 4, isn't it? So then you could say, well, this is really 4 plus root x. And that, not -4, but 4 plus root x. That would work out just fine. And then over here, it would be 4 plus x squared, using similar type reasoning. That would work as well. And so you might say, well, how on earth is that going to be the same. Well, isn't the thing I have in orange simply this? And if I'm about to square it, does that really make any difference? No, it does not. And so that's why you can consistently use that idea of axis of rotation minus the appropriate function in the appropriate form. If you want to think about it spatially every time, be my guest. I don't know that it's particularly slow or anything like that. I don't think it's bad. For me, as you can see, I kind of like to formalize this because there's just enough going on where it's like, hey, let's get all the things in their little spots, and it's good to know why that works, but I tend to just drop things in where they need to go. And I can always rely on reasoning if it seems like my system's falling apart, but I personally rely on that sort of thinking. So does that answer, is that good?
Oh, yeah, that'd be great, yeah.
Awesome. Okay, anybody else with a question? Okay, so let me